Hello everyone, this is C241 Material Science, Serdar Göktepe speaking. In this video lecture, we will continue the chapter on viscoelasticity, where we will discuss the three fundamental models of viscoelasticity, namely the Maxwell model, the Kelvin model, and the four-element model, or also known as the Berger's model. So in the Maxwell model, the spring and the dashpot, they are also known as the Hookean element, and the Newtonian element are connected in series. And in the Kelvin model, the spring and the dashpot are connected in parallel. In the four-element model, or Berger's model, we link the Maxwell model to the Kelvin model in the serial setting. In the very last part of this talk, we will consider the extension of the Berger's model towards the nonlinear form to account for more complex viscoelastic behavior of materials, especially the creep response. So let's consider the Maxwell model. As we had said, the Maxwell model is constructed by connecting a spring and a dashpot in series. Therefore, due to this serial setting, stress in the spring is equal to the stress in the dashpot. Therefore, the stress in the spring and the dashpot are equal to the total stress acting on this model. Moreover, the strains in the spring and the dashpot are different and additively decomposed at small deformations. So the strain in the spring is denoted by epsilon E, which is defined as the total strain minus the viscous strain, where the viscous strain denotes the strain in the dashpot. Okay, so elastic strain is the strain in the spring. Sometimes we denote it by epsilon spring, and the viscous strain, epsilon V, is the strain in the dashpot, sometimes that we denote by epsilon dashpot. So this is basically the main features. Stresses in the spring and the dashpot are the same, while the strains are distinct and additively decomposed. When you add them, what you obtain is the total strain epsilon. Okay. So constitutive equations. Stress in the spring is given by the Hooke's model. So stress is proportional to the elastic strain. So this essentially says that spring responds to instantaneously applied load immediately without any delay. That is the key feature of elastic spring or elastic materials. The rate of the viscous strain, on the other hand, as you recall from the first part of this chapter, is proportional to the stress through the coefficient of viscosity in the denominator. All right. So therefore, response of the dashpot to the applied, externally applied forces will actually observe through some delay. So there's a time evolution there. So you can write this expression, of course, as a stress is equal to coefficient of viscosity times the rate of the strain, viscous strain in the dashpot. So now let's consider the constitutive equation we had for the spring, okay? And in the first place, substitute for epsilon elastic, epsilon total minus epsilon viscous. So if you do so, you can write stress as E times epsilon minus epsilon viscous. And when you take the time derivative, since the Young's modulus is assumed to be constant, rate of the stress is given by E times the rate of the total strain minus the rate of the viscous strain. We can furthermore plug in for the rate of the viscous strain what we have here in terms of the stress, right? So stress divided by eta, that comes from the constitutive equation for the dashpot that is filled with Newtonian fluids. Okay, so linear dashpot. So if you substitute this expression coming from the dashpot, constitutive equation for dashpot Newtonian element, for the rate of the viscous strain, we essentially end up with this expression. There, the term in the denominator of the second term on the left-hand side is nothing but the beta, and that is defined as eta over E. This term is referred to as relaxation time or retardation time, uh, symbolizing or physically describing the characteristic time scale of the internal viscous mechanisms taking place in the material. So beta is defined as eta over E. So remember the unit of the eta is Pascal seconds, or force per length squared times time. And the unit of the Young's modulus, as you know, is the force per length squared. Therefore, the unit of beta is nothing but the time in general. We use seconds, or for longer processes, we use hours. Okay, this is the governing differential equation of the Maxwell model. This is an ordinary differential equation where we have the independent variable is time, while the dependent variables are stress or strain. So depending upon the loading, whether it is the stress controlled or strain controlled, you can specify one side of this equation and solve for the unknown part in terms of time, as we will do it for two important experiments of viscoelasticity. One important experiment is the creep test or creep experiment, in which what you do is you prescribe the stress. What you do is at time t0, let's say, you increase the stress from zero value to a finite value, sigma 0, and keep it constant for a while between t0 and t1, and then unload the material again back to the stress-free state. Okay? And during this test, this is generally done by hanging your specimen upside down and loading it with a dead load at the end, again by weighting some weight at the end of the specimen for a longer time. What you do is you actually specify the stress, right? So, and what you monitor is the deformation or the strain. And typically for the Maxwell model, we observe at time t0 when at the instant when we apply the stress from 0 to sigma 0, we observe some instantaneous elastic response that is denoted by epsilon 0. And as the stress is constant, strain will evolve linearly with a constant rate. And when you remove the load, when we unload the specimen, we observe that the amount of stress that is recovered is, strain that is recovered is equal to sigma 0 over E. That is also the instantaneous elastic response. And since stress is 0, then your dashpot remains where it is. So this is the permanent deformation observed in the Maxwell model. So if you want to decompose the strains, especially when you look at the strain time curve at T1, the recovered strain or initially observed strain, instantaneous strain, is due to the straining in this spring, while the evolution of the strain from epsilon 0 to a higher value with a constant rate is due to the separation of the dashpot. And the rate of the strain here is constant because the stress is constant, since the viscous strain evolves proportional to the stress through the division by coefficient of viscosity. This slope is nothing but the rate of the viscous strain, of course. Since this is the total strain, it is decomposed into the elastic part and the viscous part. And since this is the elastic part, which is constant for a constant stress in this serial setting, change in the strain between T0 to T1 is given by the evolution in the viscous strain. Therefore, when you unload the specimen, Maxwell model, fully at time t1, stress goes to 0 and elastic strain is recovered immediately, and the strain in the dashpot remains as a permanent strain. Okay, so this is the idea. So it remains there because you unload material to the stress-free state, When stress is 0, then the rate of the viscous strain is essentially also 0. So this can be derived mathematically as follows. In the creep test, you have the stress function between T0 and T1 equals sigma 0. It's constant. Therefore, the rate of the strain is equal to 0. When you plug in this expression into governing differential equation, we have the first term vanishing identically, and the second term on the left-hand side becomes sigma 0 over beta, which simplifies further to epsilon dot is equal to sigma 0 over eta. Exactly what we said, that the rate of the strain between T0 and T1 is given by actually the rate in the viscous strain, where the elastic strain is essentially constant. So solving this differential equation for epsilon for the initial value of the strain equals sigma 0 over E, that is the instantaneous elastic strain, we obtain the linear creep response of the Maxwell model. This is actually nothing but the equation of the line between this red line between T0 and T1. Okay? For the second part, when the stress is dropped to the 0, you see that sigma becomes 0, and sigma dot is also 0. Therefore, epsilon dot becomes 0. Therefore, epsilon must be constant. So knowing the value of the epsilon here, especially the strain in the dashpot, you actually obtain the constant strain, permanent strain in the Maxwell model. Okay, so let's consider another important test, which is the relaxation test, in which we increase the strain at a certain time, let's say T0, to a finite value epsilon 0, and keep it constant. And during this strain-controlled experiment, what we monitor is the stress during the course of the experiment as a function of time, let's say. So when you increase the strain from 0 value to epsilon 0, again, the dashpot will lock, so it cannot react immediately, instantaneously. But all the strain will be compensated by the spring. Therefore, since all the strain is compensated by the spring, the initial stress will be the initial strain, or the strain of the relaxation test times the Young's modulus of the spring. As time passes, on the other hand, when the total strain is constant, this point will move towards left, where the spring will be unloaded, it will retract, and the dashpot will open. As the dashpot opens, at a rate, at a decreasing rate, because stress is decreasing. Remember, the opening rate of the dashpot or evolution of the viscous strain is proportional to the stress. Spring will recoil and the stress will relax. And this is typically observed in viscoelastic materials and referred to as the relaxation phenomenon. And this test is referred to as the relaxation experiment. So we can solve the governing differential equation that we have derived in the beginning for the given loading. In this case, we have a strain-controlled experiment. For the t values, time values greater than t0, strain is equal to epsilon 0, and the rate of the strain is equal to 0. Okay, so if you substitute this into the governing differential equation, what you obtain is such an evolution equation for the stress. Okay, and when you solve this expression for the stress as a function of time, with the initial condition for the stress, which is E times epsilon 0, due to the fact that when we increase the strain from 0 value to epsilon 0 at time t0, the spring will be the one that will compensate that deformation. Therefore, the stress will be given by E times epsilon 0 at time t0. That is our initial condition. We obtain what we call the relaxation response of the material. Okay. So that is typically the exponentially decaying function. As you see, when t is equal to t0, we have sigma 0 that is equal to E times epsilon 0. As time passes, stress decays exponentially. When you take a closer look at this relaxation response of the Maxwell model, we observe that when you draw a tangent to the relaxation curve, stress time curve at t equals t0, the intersection point of this tangent line drawn at time t0 to the stress time curve with the horizontal axis, in other words, the time axis, gives you the position of the relaxation time. In other words, this intersection point minus t0 is nothing but the relaxation time that actually you can prove by taking the derivative of stress with respect to time, obtain the slope of this tangent, and divide this stress value by that tangent, and you should get the what we call the relaxation time. What does it mean? It means the higher the relaxation time, the slower the stress relaxation is, or the smaller the relaxation time, the faster the relaxation is. So in terms of viscosity, smaller the viscosity, in other words, when it is easier for fluid to flow, smaller the relaxation time is, in other words, the faster the relaxation is. Okay. For this exponential function, we can also observe that when you look at the value of the stress that is attained when t is equal to, or t minus t0 is equal to beta, we observe that sigma value becomes approximately 0.37 times sigma 0. That means relaxation time for the Maxwell model refers also to the time at which the about 63% of the stress is relaxed. All right. So this is what this exponential function essentially says. So in the upcoming slides, starting from this slide, we will see a bunch of movies where the behavior of the Maxwell model will be demonstrated for different kinds of loadings, for different values of the material parameters, especially the relaxation time. For the simulation demonstration purposes, I have selected the Young's modulus equals 1 gigapascal, eta 100 gigapascal a second, and therefore corresponding relaxation time is 100 seconds. Okay, so in this slide, we have the creep response and the relaxation response of the Maxwell model together. Let's first take a look at the creep response. So at t equals 40, I increase stress to the 50 megapascals and keep it constant for a while until 160 seconds and drop it back to the zero value. And this is what you observe in the strain time diagram. That is the creep response. You see instantaneous elastic, and then dashpot evolves, and then instantaneous elastic recovery, and then dashpot remains where it is. So it would be more instructive if you follow this movie with the animation of the deformation of the Maxwell model. Let's play it again. Instantaneous elastic, dashpot opens. You see spring is stationary, spring recoils, and dashpot remains where it is. In the relaxation test, remember what we do is we have a strain controlled experiment. We increase strain to a value, which is in this case 0.01 at time equals 40 seconds. And then keep it constant, and then remove the strain again at t equals 160 seconds. And then observe what happens to the stress. And this is the animation of the model, and this is the stress strain diagram. So load the strain, stress relaxes. And then when you unload, you see you generate compressive stress and relaxes in the opposite direction. Let's play it again. Boom. And then you see dashpot relaxes, therefore spring recoils, therefore you see some relaxation. So if I didn't give you the material parameters, you could actually predict them. How? Knowing that the spring is the one that reacts immediately to the applied strain, as you see here, By looking at the initial stress, which is about 10 megapascals, and given the strain in the relaxation test is 1%, you can immediately observe that 10 divided by 0.01 gives you 1000 megapascals. This is exactly what you have here selected for the Young's modulus. For the relaxation time, on the other hand, what you could do, you could actually do what we have just discussed. You could draw the tangent to the stress time diagram at t0, which is 40, and then find the intersection point of this tangent line with the time axis, and difference between the intersection point and the point at which we applied strain gives you the relaxation time. So apparently we started our experiment at t equals 40 seconds, and then when you draw a tangent here, and that will essentially goes to somewhere here 140 seconds, and difference is basically our relaxation time, which is 100 seconds. Okay, and about 100 seconds, which corresponds to t equals 140 seconds, about the 63% of the stress has decreased. So that means the stress corresponding to t equals 140 must be something like 33.7 megapascals. So they are all observed here. Let's play the here again. Elastic response in spring opens and the rate of opening decreases, and then dashboard opens, excuse me, and the spring recoils. So I'm gonna upload these movies as separate MP4 files, so you can play them over and over again, just to understand how the mechanism actually works. Another interesting example is the response of the Maxwell model under monotonic strain. So we increase the strain at a constant rate. So from 0 to 200 seconds, we increase strain from 0 to 0.02. Okay, that means a loading rate is like something like 10 to the minus 4 1/2. And this is the strain time curve. This is the stress strain curve. They are similar since strain is essentially monotonously increased, and this is what you observe in the simulation. So if you had only the spring in the model, your line would essentially go like this, okay? And when, since Young's modulus is equal to 1000 megapascals, at the value of the total strain, which is 0.02, your stress would assume the value about 20 megapascals. And this deviation from the linear elasticity, or in general elasticity in this case, is due to the opening of the dashpot that essentially relaxes the elastic response. Let's see. You see, since dashpot opens as you deform, spring doesn't deform as much as we pull the Maxwell model. Therefore, the stress strain response becomes much more compliant than you would observe for purely elastic material. Another interesting simulation is the cyclic simulation through a sinusoidal strain as a function of time. We have this strain that is applied through a sinusoidal function whose period is 100 seconds. And we apply 2 cycles, and this is the corresponding strain stress time diagram, and this is the stress strain diagram. Okay, similar observations, similar to the monotonic strain observed. Spring and the dashpot are not in the same phases of deformation. Therefore, we see some hysteresis, right? And this hysteresis is, of course, an indication of the energy dissipation, as you will see on a real material, viscoelastic material in lab number 3 in this course. Okay, so what happens if I change the relaxation time? Remember in the preceding simulations, we had the relaxation time 100 seconds. In this case, in this slide, we have the relaxation time is set to the 10 seconds on the left panel, in the middle panel 50 seconds, and the 200 seconds in the last one. Therefore, the material response on the left is the one which is the least viscous, while the one on the right is the one with the highest viscosity, since relaxation time scales with the viscosity for a constant Young's modulus, which is 1 gigapascal. So what you observe is that the smaller the relaxation time, the faster the relaxation is, as you see, right? And that is observed, for example, when you compare the first movie with the second one and the second one with the third one. The slowest relaxation is observed in the third movie, while the fastest and complete relaxation is actually observed in the first movie. This slide highlights the effect of the relaxation time, therefore viscosity, on the rate of the relaxation of the Maxwell model. So let's take a look at the influence of the relaxation time on the stress strain curve of the Maxwell model when it is subjected to sinusoidal strain. See, so this is the sinusoidal strain applied 2 cycles. You see, this is the one for the lowest viscosity, and this is the intermediate value of the viscosity, and this is the highest viscosity. So you see here, spring doesn't deform much, while the dashpot deforms faster, right? Therefore, the stress generated is relatively small, especially compared to the second movie and the third movie, the one in the middle and the right. So when you increase the relaxation time, therefore, when you increase the viscosity, you observe a steeper curve in spring deforms more, as expected. And when you increase the viscosity, the dashpot doesn't deform much, but the spring is the one that follows the loading. Okay, so as you see, as you increase the rate of the loading, or sorry, when you increase the relaxation time, you don't always increase the dissipation, but you have as a stiffer response that you observe for the Maxwell model for the same rate of the loading, for the same loading function, for different values of for increasing values of the relaxation time. When relaxation time goes to infinity, in other words, when we feel the piston with a highly viscous, extremely viscous material, as we can imagine, this curve will converge to the linear elastic response, right? So you will be going forward and backward on the same curve without generating any hysteresis, in other words, without dissipating any energy. Okay, second model we will consider is the Kelvin model. Okay, in the Kelvin model, we have a spring and the dashpot that are connected in parallel. Therefore, the strain in the spring and the strain in the dashpot must be the same. That is the constraint. And when you draw the free body diagram, the total stress will be given by the stress in the upper branch, in other words, in the spring, and the stress in the lower branch, in other words, the stress in the dashpot. Okay, so we have, in this case, in contrast to the Maxwell model, additive decomposition of the stress into the elastic stress and the viscous stress, in other words, the stress in the spring and the stress in the dashpot, but the strains are the same due to the parallel setting. So constitutive relations are essentially as usual. For the spring, we have the Hooke's law, where the stress is proportional to strain. For the Newtonian model, we have the linear viscous response. In other words, Newtonian fluid expression, stress in the dashpot is proportional to the rate of the strain through the coefficient of viscosity. So when you sum these stress expressions up for the total stress, you obtain total stress as E times epsilon plus eta times epsilon dot, where the first term is the stress contribution coming from the upper elastic spring, And the second term on the right-hand side is the contribution to the stress from the lower viscous response. So if you divide this expression by by eta, what you obtain is this version of this differential equation. So they are equivalent. Where again we introduce the characteristic time of the model as beta, that is given by the ratio of the coefficient of viscosity to Young's modulus. Let's consider the creep test for the Kelvin model. So again, the stress is applied at T0, kept constant for a while, and removed at T1. Okay, and this is essentially the response. In the beginning, we have exponentially saturating response, and when the load is removed, we have the exponentially decaying response. That is totally different from what we observed in the Maxwell model. So mathematically, you can start with the governing differential equation that we had derived here and substitute for sigma 0, which is the stress value at t equals t is somewhere between t0 and t1. And the rate of the strain is 0, and that doesn't appear here anyways. So this differential equation becomes essentially this. And when you solve this differential equation for the initial value of the epsilon, which is equal to 0. Why it is the case? It is the case because when we apply the stress at T0, in other words, when we increase the stress from 0 value to sigma 0 at time T0, the spring cannot respond immediately because the dashpot in the lower branch would lock. Okay? Therefore, this locking effect of the dashpot is realized as the initial value of the strain becomes 0. So what carries then the stress at t equals t0? Of course, stress in the spring is proportional to the opening. When it is equal to 0, a spring cannot carry any load. But the stress that is in the dashpot is proportional to, remember, the rate of the strain, right? Since although the strain is 0, the rate of the strain is actually equal to 0, but it has a finite value that you observe here, that is the slope. And this slope of the creep response is actually determined by the viscosity of the material. Sigma 0 divided by eta gives you the initial slope of the creep curve, and that gives you sigma 0 over eta. So by looking at the initial slope of the creep curve of the Kelvin model, you can actually identify the value of the viscosity. If you wait long enough, in other words, if you set the value of T1 high enough, this curve will converge to a steady state value, let's say epsilon infinity. When the epsilon is constant, in other words, steady state, there will be no contribution from the dashpot, and all the stress that is applied, sigma 0, will be carried solely by the spring. Therefore, the saturated value of this, in other words, the steady state value of the strain for a longer times of the creep will be given by sigma 0 over E. So if you carry out an creep experiment that lasts long enough, you can actually identify for the Kelvin model 2 material parameters by looking at the initial slope of the creep curve. You can identify the viscosity. By looking at the steady state of the strain, you can identify the Young's modulus, where the former is given by sigma 0 over eta, and in other words, the initial slope, and the steady state of the strain is given by sigma 0 over E. So that means in the very beginning, the total stress is carried only by the dashpot. At the very end, when the strain saturates, the total stress is carried by the spring. In between, there's a load sharing mechanism. Dashpot releases unloads certain amount, and that amount is carried by the spring. Okay, and of course, stress in the spring will behave similar to this curve, right? So because stress in the spring is proportional to strain through the Young's modulus. Therefore, stress in the spring will increase like this, while the stress in the dashpot will decrease like this, such that their summation is constant, which is your creep stress. Okay, so if you solve this expression, you obtain this for the initial value epsilon 0 equals 0. This is exactly what you have here. And when you, as you see, when you set t equals 0, sorry, t equals infinity, this term vanishes identically, and you are left with sigma 0 over e. That is the steady state value. On the other hand, when you take the derivative of this strain and evaluate it at t0, you will see that this is going to be the sigma 0 over eta, which is nothing but the initial slope of the creep curve. Okay, so similar to the relaxation time, we can also define the retardation time. All right, so in the Kelvin model, when you draw a tangent to the creep curve at t equals t0, intersection point of this, or the time value corresponding to the intersection point of this initial tangent with the steady state strain line, horizontal line here, gives you a point whose difference between the initial time t0 is nothing but the beta. And this time is referred to as the retardation time. In other words, the delay time, because essentially what you have here retarded is actually the elastic response, because when you wait long enough, what you obtain is the saturated strain epsilon infinity, and that is nothing but the elasticity. Okay, therefore it is sometimes referred to as retarded elastic strain. Okay, similar to the Maxwell model, we have some movies here. In the first place, we have the Kelvin model under monotonic strain. You see, in this case, we apply strain increasing monotonically, and the stress has initial values which is equal to 10, and it essentially increases. Increasing the stress, in this case, given by the spring. The instantaneous response of the stress is, on the other hand, given by the dashpot. Why? Because the rate of the strain is constant, even at t equals t0. Rate of the strain is constant, therefore viscosity times the rate of the strain gives you the initial stress, that is the rate of the strain, in other words, the slope of this line, which is 10 to the minus 4, times viscosity gives you, which is 10 to the 5, gives you the initial stress, and then the increase in the stress is governed by the spring, whose slope is, of course, in the stress strain curve, gives you the Young's modulus, right? This is the creep experiment we just considered. You see how the creep stress is applied. Stress is applied, constant, and then strain evolves. And then when the stress is removed, it starts to decay. Let's play it again. Then decay. So for relaxation time 100 seconds, we have, when you draw it here, essentially this curve, tangent to the curve, you observe this curve goes somewhere here. When t equals 100, it comes somewhere here. So that means if you waited long enough, this creep curve would converge to somewhere. Can you identify the position? We can identify the position. The applied stress is 50 megapascals, all right? And the Young's modulus is 1000 megapascals. Remember the derivation we have here. The epsilon steady state is given by sigma 0 over E in the creep test, right? And 50 divided by the Young's modulus, which is 1000, gives you 0.05. So the epsilon infinity is somewhere here, 0.05. So under cyclic loading, we have such a response for the Kelvin model, which is interesting. And for the sinusoidal strain, we have such a response. Remember, in the sinusoidal strain, we have an uninclined, actually perpendicular, circle-like response of the dashpot. Presence of a spring gives you some inclination for that response in the sinusoidal loading. This is also an interesting observation. Another interesting observation is that in Kelvin model, as you observe, we didn't mention anything about the relaxation response. The reason is, if you recall the relaxation experiment from the Maxwell model, where we apply constant strain, okay? Strain is applied at t equals t0, and it varies from 0 to epsilon 0. So at this point, at t equals t0, rate of the strain is like infinity, all right? Therefore, when you have rate of the strain infinity, in the Kelvin model, the amount of stress that you need to apply to generate such a constant strain, epsilon 0, is infinity as well. Therefore, that is, you can do it practically by applying a very high stress to generate constant strain, but it is not exactly what we theoretically see here. So you, in the first place, always apply strain at a finite value. And higher the rate of the strain, the higher the initial stress will become, of course. For the Kelvin model, we analyzed the creep response at for different values of the retardation time, beta. You see, smaller the retardation time, the faster the convergences. As you see, epsilon infinity is achieved here, 0.05. And for the greater value of the retardation time, you see the relaxation is slower. Sorry, the creep is slower. When it comes to sinusoidal loading, you see here, as the contribution of the dashpot decreases by decreasing the viscosity, we see a smaller hysteresis. In other words, a smaller dissipation, smaller amount of dissipation, and less magnitude in the stress. And when you increase the retardation time, stress response actually becomes stiffer. Okay. In general, when we talk about relaxation and creep, we consider Maxwell model for relaxation experiments, where we have exponential response, and Kelvin model for the creep response. So in creep, we can combine these two material models to generate what we call Berger's model. So in the Berger's model, we have the Maxwell model that is serially connected to the Kelvin model. So the motivation is that the viscoelastic behavior of materials in reality is relatively complex. And these two models of viscoelasticity, Maxwell model and Kelvin model, can explain only minor effects, basic features of viscoelasticity, and they generally become inadequate when you like to model real viscoelastic material response. So Maxwell model represents the viscous fluid through its full relaxation to the stress-free state, because when you, as we have seen, when you conduct a relaxation experiment, a dashpot relaxes fully, and the Kelvin model represents a solid through its saturated creep response and retarded elasticity. So since spring keeps carrying the loading, this is a typical solid-like response. All right, so this is an important observation as well. And when you consider the Berger's model as a combination of these two, and especially the creep response of the Berger's model, we can combine the creep response of these two materials. So the creep response of the Berger's model can be expressed as the creep response of the Maxwell model In the exploration at the bottom, the first two terms on the right-hand side represent the creep response of the Maxwell model, remember, linear, and the instantaneous elastic. And the exponential one is due to the Calvin model. So in this diagram, for t0 equals 0, we observe this. When you apply sigma 0 at time 0 and keep it constant for a while, what you observe is this elastic response, instantaneous elastic response due to the spring in the Maxwell model. And then we have the combination of the viscous part of the Maxwell model and the Kelvin model, viscoelastic Kelvin model, contributing to this increase, all right? When you unload the model at certain time from t sigma 0 to 0 stress value, we observe immediate elastic recovery of the strain that is due to this part. And when you wait for a while, certain part of the strain is also recovered. That is due to the retarded elasticity in the Kelvin model. And a certain part will remain there as a permanent strain, and that is due to the viscous element, the dashpot in the Maxwell model, this term. So that means when you look at the creep response, there are three terms. First term is the elastic term, that is instantaneous elastic response due to the spring, and that is recovered immediately. We have another term due to the Kelvin model that is recovered with certain time, that is recoverable but not instantaneously, but in a retarded fashion. And the term in the middle represents the strain evolution in the dashpot that is permanent. When you unload your specimen to the 0 stress value, strain that has developed in the dashpot will remain as a permanent viscous strain. Okay, this is an important observation. So you can take the Berger's model to generalize it towards nonlinear creep response by adding here an exponent n and the coefficient mu and another exponent alpha and maybe another coefficient here, let's say q and k. So these are just generalizations of what we have in the here in the original parent representation of the Berger's model. Okay, so people sometimes use this model to fit creep response of real materials. So with this, we are pretty much done with the chapter on viscoelasticity. In what follows, you will start to consider properties of materials related to their strength, especially brittleness and ductility, toughness and resilience, and the true stress and true strain, and so on. I talk to you later. Bye-bye.